start the recording. Okay, so welcome to this fifth lecture on fractals. So this will be the third lecture on fractals, or 2.5-ish lecture on fractals. And so last time we've seen many different things. So the first time, first half hour that we did on fractal, we kind of introduced the Koch curve as a way to represent coastlines and their fractal nature. And then we explored how can we describe this Koch curve and the fact that a fractal is related to a power law, and the fractal dimension is related to the exponent of this power law. So by observing a phenomena, finding a power law relations between two variables in the phenomena, you can express the fractal nature by fitting the power law and finding out the exponent. So in this way, you can kind of find out the fractal dimension of the phenomena that you want to describe, and this is kind of quite universal. And then we've seen different way to define this fractal dimension. One is the box dimension, the other is the Hausdorff dimension, a little bit more complicated. Box dimension is based on boxes, or box counting, so the counting of little squares or boxes in n dimension that cover your set that you want to cover, your fractal set. And by studying the relations between the side of these boxes and the volume of the boxes itself in a dimension, you can find out the dimension of your object, that for smooth figures, smooth sets, these would be directly related to the simply the dimension in which your shape lives in, if it's 2, 3, 4 dimensions, whatever. In the case of fractal, since you have a non-trivial relation between perimeter and surface, and the perimeter, if you take your yardstick length, so your side of the box that goes to 0, the perimeter goes to infinity. So that's a property of the fractal, and that's a very nice, interesting properties of fractal. And this is why they come up so often in physics, because it's a way that nature has to maximize the volume, to maximize the surface, keeping the volume contained. So many things in nature works regard the interplay between surface and volume, in biology especially, but not only. And this is why this power law appears so often in nature. And then we've seen the Hausdorff dimension. It is a slightly more complicated way that for the mathematically advanced of you is related to the theory of measure. So it's like what you do when you calculate the Hausdorff dimension is taking spheres of a given diameter, and then again taking diameter to 0, but you look at the measure of these spheres at the s-dimensional measure, and then you find out which is what is the dimension. Then we calculated the Von-Koch curve with all these things, and we find out the relation between box and Hausdorff dimension. And then we introduced the Cantor set, which is a very interesting counterexample of many things in mathematics. So the Cantor set is obtained by kind of dividing your set in interval from 0 to 1 in 3 parts, and then taking only the first 2 parts, the first part and the last part, and leaving empty the interval in the middle, and then continuing these procedures forever. And what you obtain is a very interesting mathematical object, which has 0 measure. The length of this object when you go for an infinite number of iterations is 0, as you can see here. I think you see my mouse, right? So it's a little bit easier to point here. So you see that this object, the length of this object goes to 0, but nonetheless can be mapped in one-to-one correspondence to the full interval, to the dense interval from 0 to 1. And this can be seen in a floating point configuration, either base 3 or base 2, depending on how you arrange the Cantor set. So you can just take this. So that's a very interesting mathematical object because it is taken as a counterexample to many things. I don't know if you've seen this in other courses, because it's used a lot in mathematics. So if you have a lot of mathematical background, this might be the 5th times that you see this object. But I know that this course is very heterogeneous. So there are some of you that are second-year students and some of you that are PhD students. So that's a further challenge of keeping it interesting for everyone. But chaos helps because there is a lot of things which have a deep mathematical meaning, but they can also be appreciated from a more superficial, if you want, standpoint, from a more phenomenological standpoint. So Cantor set is one of those. So it's really mind-blowing, the fact that you can map the interval from 0 to 1 that has measure 1 to something which has measure 0. I suggest you to think about this over the weekend. And yeah, I hope that this was interesting. It's an interesting example. So if I wrote right here, so if I reproduce the Cantor set here, you should see it, right? Can you see it? Or it's wait that I stop the sharing of the screen. Okay, so now you see me large. And if I do something like this, you see it, or you need larger? You see it fine? You have to tell me, yes?
That's right. That's right, yeah.
Okay, so if this size is fine, I will take this and larger. I will try to keep it a little bit like this. So if we want to reproduce the Cantor set, so this is L0 is equal to 1, and then we can split it up in third. So here L1 is equal to 2/3, and then we split this up into thirds again. Okay, so L2 is equal to 2/3 to the square, and so on and so forth. You arrive to a set which has this length that goes to 0 for n that goes to infinity. So after many steps, the length of this, the measure of this Cantor set will be shorter and shorter until finally we'll go to 0. So you see it also, because before was chiral symmetric. The 0 and 1 was, you could read it. Do you see it straight, right? Because I see it mirrored, but I think you see it straight. The resolution is not good enough for subscripts. Yeah. So I will keep the subscript a little bit larger and the upper script a little bit larger than the usual notation, hopefully. So this is 0, this is 1, this is 2, of course, this is n, and this is to the n, and this is n that goes to infinity. Okay. You can switch, so you don't need to close. Okay, I will try this during the break, maybe, because this will help me a lot if I can switch dynamically between the two. Okay, so that's a fairly interesting piece of mathematics right there. But the thing that we're interested in right now is the fact that this very special Cantor set can be represented by maps, because there is a correspondence between what we studied before, which is one-dimensional maps, and what we are studying now, that are the fractals. So this is why we did maps before, because it's a very good piece of phenomenology that can represent fractals. It can represent chaos very well. It's the epitome of chaos, but also because it's something that appears over and over. So this is why I prefer to start from maps. and not from non-chaotic phenomena. And so, for example, fractals can be represented by maps. I see that it has some difficulty with focus, but I hope that it keeps it. Okay, so in this case, we have basically an object which lives in a one-dimensional space. It's only the interval between 0 and 1 that is populated by pieces of the Cantor set. And we found out that the box dimension, did we? No, maybe not. Did we find out? Okay, well, if we didn't find out, I don't remember if we did it last lecture, but it's a good exercise. I don't want to give much time to this because it's kind of, it's almost trivial, but you can calculate very easily from this that the dimension is, sorry. Of course, the dimension will be related to this factor 2/3 in the same way that was related in the case of the Koch curve to the factor 4/3. So this little interval can be covered by boxes of the same size, and we'll basically get the length will be the volume of the boxes that you need to cover, and the length will go to 0. And therefore, in a very similar way to the Koch curve, you can find out that the box dimension is equal to the Hausdorff dimension of the Cantor set, which is equal to the logarithm of 2 divided by the logarithm of 3. And that can be demonstrated. I will not do it, but the interesting thing is that this is less than 1. So in the same way that the Koch curve was living in 2 dimensions, and its dimension was between 1 and 2, in this case, the Cantor set is living in 1 dimension, but it reduces the one-dimensional set that has measured 1 to a set that has measured 0. So it still keeps a one-to-one correspondence with it, but the measure gets decreased to 0. So the dimension of this fractal set would be between 0 and 1. And as you can see, you have this number here that is between 0 and 1. Okay, so one thing that is interesting to study is the map that constructs this set. And the map is basically made by 2 pieces. So in the same way that I described it to you, that you have to take the interval and then split it into separate pieces, you have to do the same when you construct a map. So you have to consider a piecewise map in any case. So something which has a certain value when x is smaller than 1/3, and has another value when x is larger than 2/3. So in this case, the 2 pieces are these ones. So I have a first piece, S1, which I define by the fact that x prime takes x and maps it to x divided by 3. And then I have a second piece where the next iteration is given by taking a given x and map it to 2/3 plus x divided by 3. So I have this piecewise definition where, depending on your x, I can either map it to this interval here or to this interval here. Okay? So given a given x, I can map it to these 2 paths. And then the map is given by the union of these 2 possible maps. So n, the map for n plus 1 is given by S1 for the map in n, union S2 for the map at the iteration n. So what happens is that I take a set at the given iteration. So if I have at the first iteration 0, F0 is simply the interval 0 to 1. So this is the set F0. And then I put S0 into this 2 interval, and I split it in 1/3 plus 2/3 0, okay? So if F0 is defined like this interval, and then I apply this map, F1 is defined as the interval 0 to 1/3 united with 2/3 to 1. And then F2 then will be the same. I will have to apply these 2 intervals to these two maps, and this will give me a lot of intervals. Okay? This will be 4 intervals that I'm too lazy to write or calculate. But I hope it's clear. So if you construct a map like this, and then you take n to infinity, then you can derive, you will have that f of n, of a given general n, is the Cantor set at the given iteration n. And if you take n to infinity, you will get the famous Cantor set, total Cantor set. Okay. So, clear? Yes, I don't see any questions. So again, if you have questions, don't hesitate to turn on your microphone, wave, do something. Okay. So, in other words, what happened now that I formalize it as a map, I can study it in a better way. I hope, even if it's not, if you cannot read, please write it. Okay, so now that I formalize it in this map, then I can study how this map acts on my intervals, on my sets. And the important thing to calculate is the contraction. So the interesting thing regarding fractals, as you can see here, regarding the Cantor set in particular, but fractals in general, is the fact that they take a set that lives in a given number of dimensions, and then by iterating a given map, they reduce its measure. So this set has measure 1, and by iterating into the map, I will reduce its measure to 2/3, 2/3 to the square, sorry, 2/3 to the n, and it goes to 0. So what this map does, or what the iteration that enables us to define the Cantor set do, is contracting the original intervals, the previous interval. So you have an interval that has measured 1, and then you contract it by 2/3 at each iteration. So you have a contraction that stays the same. So the idea is that if you take the map, your map S at a given iteration I for a given X in your interval, and you subtract the S for your X prime for the interval you map it to, okay? And you take the absolute value, this will be a certain Ci of the distance between these two values, between the value that you start with and the value you contract it to. So if you wish this, you can put a +1 there. So if you do like this, then you have this parameter Ci, which gives you the contraction. Okay, in a given, so this Ci, I hope it's not confusing, because this is not n, okay? This is not n. This is S1 or S2, okay? So you can take this Si, so this is S1, C1, in this specific case, this is S1, and this is S2, okay? I have these two pieces in my piecewise definition. So it's not an iteration like this, but this represents the two pieces. In this definition, in this specific case, in this in the Cantor set, I have only two pieces. But in general, I can have I pieces. I can split this instead of splitting in 3 or 2 parts, according to how you look at it. You can split this in 5 parts. I don't know. You can generate another set that will have a different shape and a different fractal dimension, and then you will have more factors here. But basically what you're doing here is to calculate the distance between the application of one of these two pieces before and after the application, okay? The distance between two pieces before and after the application. And saying that this is equal to some contraction. So this is not a given. In the case of the logistic function, at each iteration, you will have a different contraction. This is what gives you the complexity of calculating the Lyapunov exponent for something which is non-trivial, for a map which is not trivial. But in this case, the C's are constant, okay? Is it pretty clear? So in this case, my Ci's of the Cantor is equal to 2/3, because both S1 and S2 are splitting X in thirds. Clear? Sorry, to 1/3. Is it, I cannot see you very well. You look very clear, very clear. Okay, so so it's equal to 1/3, simply because if you substitute, you have this X divided by 3. So you substitute here, you will have X prime, that is X prime divided by 3. And you can have a factor 2/3 plus or minus, but this will not reflect in your difference, will be cancelled by the difference, and you will be left with 1/3. So your contraction factor is 1/3. So what you have now, the interesting thing of acting in this way is this, that you can define, there is a theorem that I will not demonstrate here, and I mean, it's not matter of the course, but this introduction of the Cantor set gives you an intuition why is that and why this works. That the whiteboard is smaller than the usual lecture hall. So let's see if I can emphasize this. This red is not very bright, but okay. So the theorem states that the sum over I, over all the pieces of the contraction factors related to each piece, elevated to the fractal dimension D is equal to 1. So if you wish, this is another way of defining the fractal dimension. So in this case, it's pretty clear. So you have two factors here. So you have that are both 1/3. So in the Cantor case, you have 1/3 so you have the sum for I that goes 1 and 2 of 1/3 to the D is equal to 1. So then it follows that the dimension is equal to this. Okay? In the case of the Cox curve, so let me delete this, because I hope you kind of guessed that this is the different pieces. So we can study another example. In the case of the Cox curve, I can pull up a very similar definition, but I will have 4 pieces, because in the Cox curve, I take the interval 0, 1, and I map it to something which has length 4, okay? So I take it this, and I split it, and then I make the equilateral triangle. So this was, I hope, it's very clear as well, how you could write the Cox curve in this context. I will not do explicitly, but it's very intuitive to think that it works exactly the same way. You have these interval, and then you split it to 2/3. The only difference is that instead of leaving this empty, you go into this other dimension and you build up. So your contraction factor is still 1/3. So your map would be very similar. You take this and you split it, and you take the interval 0, 1, and you split it to 1/3, and you split it to 2/3, 1, and then you split into 2 other pieces. So you have 4 pieces, each of which has a 1/3 contraction. So let's delete this. So in the Cantor case and in the von Koch curve, so basically what I have are CIs where all the CIs are still equal to 1/3. This is not for all fractals, it's just 2 very similar examples. So the CIs are still equal to 1/3, but now the I is not only 1 and 2, but goes from 1 to 4. So I have 4 pieces. So it follows that the dimension calculated in this way will be logarithm of 4 divided logarithm of 3. Okay? Sorry, I'm covering it. Yeah, I think you can see everything I've written, and that's fine. So the interesting thing is that since this relates to basically the measure, because it's all based on the contraction of the measure of your set. So basically this D, which I haven't specified, is the Hausdorff dimension. and this as well. So this is all a reasoning that is defined by the contraction of a metric, and I defined before the type of dimension the taxon the measure is the Hausdorff dimension. Okay, so you can demonstrate it formally, of course, but I hope this is more up your alley. It's a little bit more fun without getting lost in the mathematical details. And of course, if you're interested, you should have a look and try to derive by yourself. Okay, is this clear? Do you have questions now? Waiting for questions.
Yes, I have a question.
Mm-hmm.
Could you quickly repeat how this can be described using binary or other numerical bases?
Oh, yes. So with binary, my personal taste is that with binary, it's really intuitive. So my personal taste is that with binary, it's a nice mathematical point. But do you have questions about what I just spoke about, the dimensionality of the Cantor set and the fact that it can be derived in this way and mapped in this very interesting piecewise method? Can I clear the whiteboard? Yes. So the variance with the iPad whiteboard, there's a finite space in which I have to leave. Okay, there's a finite metric, if you will. Okay. So it's really interesting to see how this can be mapped to binary or ternary bases, and it basically follows the same reasoning. I mean, so to map it into binary, I think this is more intuitive, in my opinion. It's simply that what you're doing, you're mapping this continuous interval 0 to 1 into a series of either 0 or 1 choices, into two choices. And here, which are the two choices? Very clear. So you go either, if you look it from like a person perspective that is looking this in a straight line, so it's in front of the Cantor set, and you think like a child would think of this object. It's something that gets split, and then you can either take the left or the right piece. Okay, you can either go left or go right. It's a series of bifurcations of on a road. Like you can either take one piece left or one piece right. In the same way, formally, I define it as maps with the map and the piecewise definition. I have the two pieces. I can take either S1 or S2. I can map the interval either using S1 or S2. And then I can keep taking only one of the two pieces. And then I can, that correspond to choosing if to go left or if to go right. And then I can follow this left-right forever, because this is an infinite series. It's nothing that is going to stop n for going to infinity. In fact, it's exactly what I do when I find out the definition of the Cantor set, of the full set. The full set is the iteration of this procedure to infinity. And that gives me the proper Cantor set. So by building it in this way, it's really, it's quite clear that you can go left or right, and iteration after iteration, you will make a distinct left or right choices. So this is either left, 0, or right, and I put it corresponding to 1. This is either 0 or 1, and this is either 0 or 1, left or right. And that I can go on forever. So let me draw it in a different color, so not to confuse with the numbers. So this is 0, because it's the only choice I have, but then from the first step onwards, I always have a left or right choice. Any sub-interval still has both left or right choices. And then I can go on and on forever. And if I go on and on forever, this corresponds of writing something which has infinite bytes. This is infinite bits. Okay? So this is, you can use this to represent it in a floating point notation at 0, you can tell me left or right. Let's go right, 1. Then let's go left, 0. Let's go here, left or right. Let's go right, 1 again. Let's go right again, 1, and so on and so forth. So this will be a floating point binary representation of your number, and this can be converted to decimal and have a way to write any number in the interval between 0 and 1, okay, in the decimal notation. And that's it. There is nothing more to it. So this demonstrates, exactly this demonstrates that there is a correspondence between the Cantor is homeomorphic to n, so the binary space of n possible choices, that in turn is homeomorphic to the interval of 0, 1. Clear?
I have a question or a thought.
Yeah.
Could you use this argument to show that the set of all binary fractions is homeomorphic to the interval 0, 1?
Binary fraction. What's a binary fraction?
Like a half, a fourth, 3/4, 1/8, 2/8, 3/8, 16th, and so on. Isn't that, if you start writing a decimal like 0.10111010, that's a series of binary fractions.
That's a series of binary fraction. But binary fraction, you mean like
a half, a fourth,
it was 1 divided 2 to the n, or what?
Yeah. But also
that's
2 over that, 3 over that, 4 over that.
So this is more than this, okay? Because if I take 0.01 and I take 0, 0 forever, then 0.01 is not 1 divided by 2 to the n.
No.
It's 1 divided by 10.
Oh, then I don't understand.
You don't understand.
I thought that decimal representation was in binary.
Yeah.
So how is it 1 over 10?
So how do you translate your binary numbers to decimals? That's something that of course, I don't remember, but
I think, doesn't 0.1 mean 1/2?
In this case,
yeah.
Yes, this one has, and that's okay. But there is a way to write 0.1 in decimal. numbers. This is exactly what the computer does. Don't let me calculate it right now, but I mean, you have 0, this is binary, and this is decimal. So 0, 0, 1, 1, and then you have 0, 1, 0 is 2, 1, 1, 1 is 3, right? 1, 0, 1 is 4, and you go on until you find out what 10 is, and then you write the 10 here, and then you continue with zeros, and that solves your problem, right?
Maybe I'll just write it down and email you.
Okay.
When I thought about it a bit more.
Okay, that's an option. I can also email you, I can put it in the description of the course, a link that tries to explain this better than I'm doing. I think I can find it, or I can write it. If I cannot find it, I write it, and I try to be more descriptive. But on the book, there is explain the correspondence of this to base 3. So to base 3 is basically exactly the same thing, but you keep the information about the middle, the empty middle. So it's a similar mapping, but you can map it instead of base 2 binary, you can map it to base 3. And this is explained in the book. So you have, you can go there and fetch it. Okay? Good. Are there other questions? You have, is there anybody else that has difficulties with this concept? No? Somebody wrote no, but most people are not doing anything. I don't know. 2 no's, okay. So I start to delete this, but I will put some info on the course webpage, on the Canvas thing. Okay. So now let's keep this, but I definitely understand you, because it's this Cantor set is used a lot in mathematics, precisely because it's definitely not intuitive, and it's actually challenged your understanding of mathematics, precisely because from the intuitive understanding of, for example, now we will see with the Devil's Staircase what continuity means, what continuous means, challenging this understanding of what continuous means. One thinks, okay, this is trivial, and it's continuous when I can draw it without lifting my pen. But then I can, using the Cantor set, I can define a function which is continuous and derivable, but as infinite number of discontinuities in a finite interval. So that's the funny thing. And so let's do this before going to break. Then you can discuss it during the break. And this is also important, both the Cantor set and this Cantor function, or also known as Devil's Staircase. Also known as Devil's Staircase, will appear again in the treatment of chaotic systems, and will reflect in coupled oscillators and the Arnoldi tongues. So there are many fun things you can do with chaos, but this, since this is a very paradigmatic fractal, and it's a very simple one, will appear often when we think about and write about chaos. So there are several ways, more or less formal ways of defining the Devil's Staircase. I will go with the very physics way, because that's what the book uses. and that's the intuitive way. So if you think, it's hard to see the red. Yeah, sorry, this is only a title, Cantor's function. So I will not use it anymore. So if you think of depositing on my intervals in this iterative definition of the Cantor set, some mass, something that is as mass 1. So you deposit one mass on this first interval, okay? Good. So if you deposit mass 1 on this interval, you will get at the 0 iteration, your density will be mass divided by length, in a sense. And then in this case, the mass is 1, the length is 1, so rho 0 is 1. If I do it next iteration and I put the same one quantum of mass on this interval that now has length 2/3, then this again mass divided by length 1, and this length is 0, and this is 3/2. Okay? So basically, what I'm doing here is define the reciprocal of this length and sets, of the measure and sets. So I'm defining a density measure, if we want to go a little bit more formal. A density measure for a given iteration, this would be 3/2 to the power of n, if for given x belongs to the Fn set that I defined before, so to these intervals, or 0 otherwise. Okay? So that's a fairly simple definition, but the interesting thing is that if I define a function or a distribution, so this is for the grown-ups among you, this is the way that you can define a distribution, and then you can find your density will be a distribution, and then you can define a functional distribution in your theory of distributions, defined on this Lebesgue measure of the intervals that as the integral between the interval 0 to 1 of your density for a given iteration n of x prime in the x prime. So this is a way of defining it. So for the let's do it. Yeah, it's in very small here. I hope you can see. So if we do, no, well, let's do it a little bit larger here. So this, if we do it for 0, so I will use the red, but just for a very trivial case. So rho 0 would be just rho is 1 everywhere. So rho 0 would be just like this. And the function will arrive to 1 here on top. 1, 1. Okay. In blue, if I draw rho 1 will be 3/2 the density inside this interval and 0 outside. So if I draw this, this would be a different slope because it would be 3/2 slope. And then when it arrives to 1/3, I don't have any more density, so the distribution integral will stay flat. And then we rise again to reach 1, 1. And then, I don't know about the green, so I can go these on and on forever. So this would be like this, yeah, it's not very good, but so this would be like this. So this is more slopey. Okay, I think it's pretty bad, the drawing, but on the book you find a better one. So I don't know how much can you see, but this would be row 2, and the blue one would be row 1. And you can go on and on forever. And if you go on and on forever, then every time, at every iteration, you will add more slope and for a shorter and shorter interval. So if you go on forever, what you find out would be a very special function, which is called the Davis staircase. So d of x, Davis staircase, is equal to the limit for n that goes to infinity of dn of x. And the special thing about this function, well, it has many special things. This is why it's used very often as a counterexample. So it is continuous because it doesn't have any discontinuities. If I define it like this in the distribution sense, then rho is a given piecewise function, but its integral is continuous. And it's also derivable, because I can do the derivatives of this, and I will get rho of n. But rho n, for n goes to infinity, will be 0, almost anywhere. So it's continuous, it's derivable, and its derivable is equal to 0 almost anywhere. So that means anywhere except in an interval, in a measure, in an interval, in a set of null measure. So this is continuous, derivable with derivative 0 except in an interval of null measure, but it has infinite number of discontinuities, because if you take this to infinity, each of the steps of this function that are infinite will be a discontinuities in a sense. Okay, so even if it's continuous, because in the sense of the distribution is continuous, you can derive it, and it has infinite number of discontinuities. So really plays on the definition of continuity. So it's not a mathematics course. You can define continuities in several different ways, and the way that define continuity, this is a continuous function, and the way that is defined discontinuities, this is also an infinite number of discontinuities, but the discontinuities are also in a null measure interval. So it's continuous almost anywhere, and that satisfies many definitions of continuous. So it's a good way to construct this Davis staircase, and it's a good intellectual tool to kind of make you think of the fact that even something as simple as this has kind of deep meaning and challenge your intuitive grasp of these mathematical objects. Yes, Johan? I don't hear you.
I was just testing, never mind.
Okay. Okay, so I think we can go to break now. We can discuss about this during the break. What should we do? Should we do? Unfortunately, we still haven't touched upon the Julia and the Mandelbrot set, and we have an hour. So can we do a short break of 5 minutes in the breakout room, and then the additional minutes to kind of collect us again? Okay, it's a short break. And then you can discuss this. Okay.
Can I ask you my question in the break now?
Yes, of course. Let's resume the recording. Sorry? Sorry, somebody said anything? So I think I have to pin this, pin video. Perfect. So it's slightly different now. For this hour, I have to move it a little bit. And this is up to here. Okay. And to move it to connect it to the power source, to connect the webcam to the power source. Okay. So now we've seen the Cantor set in many different ways. We mapped it to a set of piecewise maps, and we studied the if dimension. So we had a little bit of fun with that, but the fact is that the relation between maps and fractals runs deeper than piecewise function. In fact, fractals appear anytime you iterate complex maps. So if you take a one-dimensional map, but in the complex plane, so you say, no, we didn't do it with parentheses, we did it like this. Z of j plus 1 is a function of z of j, okay, where z of j belongs to z, not to z, to c, to the complex number, and f in this case is a function that takes a complex number and maps it into a complex number, of course. Okay, it is a bit unfocused, but that's okay. So that goes, yeah, like before. Okay, it's a little bit more. Okay, good. So when you iterate a complex map like this, you can make appear fractals, and now we will see how and when. So as usual, as with the one-dimensional map, you can define a fixed point when, if you apply your one-dimensional map to the fixed point, it stays in the fixed point. So this is fixed point. And then you can define the fixed point, I take it with tilde, of the nth return map. So f is the first return map, f to the n is the nth return map. So this is fixed for n return. Okay. So in other words, is periodic. Okay. So if, just like for the real maps, for the real one-dimensional map, if we take the nth return map and calculate the derivative at periodic points, and this is greater than 1. So if the derivative is greater than 1 at a periodic point, then it's a repelling periodic point. Okay? So now the Julia set, let's write it in blue, is the closure of the set of periodic points. So in a complex map, I will not only have single points, or not always. What can I have is a whole set of periodic points. I hope it's not losing too often the focus. Can you follow pretty okay? Tell me if you have problems. And so, okay. stop me if you have problems and you cannot see. So what does it mean, the closure of this set of periodic points? So for example, let's take this example as example, the quartic map. Okay. You can demonstrate, the nice thing, this example is taken very often, because the nice thing is that you can demonstrate that this is called quartic map. Because it's quadratic in the complex plane, so it's quartic. The nice thing is that you can demonstrate that this is equivalent to the logistic map. So if you remember, in the real numbers, the logistic map was x, or a factor in front, rx, x minus 1. Okay, so these two are equivalent. And there is an exercise about that. So that's, I leave you as an exercise. And if you cannot find out why, you should go to the exercise session and ask Alex. So this is an important exercise. And okay, so let's consider as the title of example, C equal to 0. So this is an example. Another example, even a subset of this example is the case where C is equal to 0. So I consider the complex map that is simply Z squared. Okay. So if I consider this complex map, there is a reflection, but I hope you can see, but it is very easy. Fz equal to Z squared. So if I consider with this example, what happens? So what happens really depends on the Z, where I start. So how maps works, I iterate this, and then I apply. So if I take some Z0 to be equal to some numbers, and then I found out F1 will be Z0 square, F2 will be Z1 square, F3 will be Z4 square, and so on and so on. Z3 will be Z2 square, and so on and so forth. Okay? So if I take Z0 within the unit circle, so the module of S0, unfortunately, I'm impossible. Let's, whoop, Fosbury jump. So now you don't have a, no, you still have. Whoop. You're missing my athletic performance. You always have this reflection, this annoying reflection. What about now? Better? Maybe, yeah. Okay, so I hope it's readable. If it's not, tell me. So Z0, the absolute value of Z0 is less than 1. So what I'm doing, let's do it here. So this is the complex plane. So, and this is the unit circle. So this is 1. So if I take this case, Z0 here, inside here, what will happen is that I will take Z1 will be Z0 square. And okay, if you don't remember your complex number, I don't know if you should be here, but just to remind you, the Euclidean notation of a complex number is this, right? So if the module of Z0 is less than 1, so the module of Z1 will be simply the square of the module of S0, of Z0. And so if it's less than 1, it will be smaller. So Z0, if Z0 is here, So if 0 is here, then what happens is that Z1 will be closer to the center with a different angle, and then Z2 will be still closer to the center, and this will approach quadratically the 0. So if Z0 is equal, is less than 1, so Zn will go to 0 for n that goes to infinity. Okay? We go to 0 in a bit of a regular way, complicated maybe, but we always go to 0. So what happens if the module of Z0 is greater than 1? So what happens in this case is the same thing. This will start from somewhere in the complex plane, larger outside the unit circle, and what will happen will be that this will roam around, but the module of Z1, Z2, Zn will increase because will be quadratic, no? Will increase quadratically. So this will go to infinity for n that goes to infinity. Okay? I don't know the angle, I don't care, but the important thing is that this will go to 0, this will go to infinity. And what else? What else are we left with? We are left with something on the unit circle. Z0 is equal to 1. So in this specific particular case, what happens is that the doesn't matter which n, I can iterate always, but these will stay on the unit circle because then the modulus of 1 square will stay 1. And so we'll continue to stay on the unit circle, but we'll travel around, okay? So first iteration will be here, second will be here, third will be here, fourth will be here. Okay, and there are a few things that can happen then. So it can be that this traveling around, it's non-periodic, so will never happen twice. This will never fall down twice at the same point because you picked a number which is when you do this square, you simply multiply by 2. You simply multiply this angle by a number over the iterations, and if you pick some strange number, that can happen that this will never come back to the same value. So we'll continue, go around and around, exploring different points each time. Another option is that you pick an angle here that when you iterate it, this will go around for a while and then fell down exactly on the same point, some periodic condition. So this unit circle is very special because it's the only one that contains periodic trajectories of this set. So the Julia set in this specific map with the quartic map for this specific condition for C equal to 0, the Julia set is the unit circle. And then, I know that you told me not to write in red, but it's such a useful color. So this is defined, the thing that is inside the circle is defined as the basin of attraction. Because if you put a point here inside the unit circle, it will fall down to your attraction point, which is 0. Okay? So 0 is your attractor. So 0 is called the attractor. The unit circle is called basin of attraction because inside of the unit circle, your map will go to 0 for n that goes to infinity. And outside here, this green area, all this green area, okay? So in this, in this green area, it will go to, if you put a point there, it will go to infinity. So this is also a basin of attraction. So this is, let's do it like this. So this is also a basin of attraction. Can you imagine what is the attractor that corresponds to this basin, that is the green one? Does anyone has any idea? Can you write it in the chat? Let me know that you're following me and not sleeping. 0. No, unfortunately, it's not 0. I mean, I don't know if I'm explaining correctly. So there is one basin of attraction that is inside the unit circle, and in this case, the attractor is 0 for this specific basin of attraction. There is another basin of attraction, which is the green side. It is outside of the unit circle. And if you take it outside of the unit circle, each of the points outside of the unit circle will also be attracted by a point or a set of points. Infinity. Thank you very much, Elias and Jongo. So infinity, if I can, I mean, it's a little bit strange or unprofessional maybe to write it on the blackboard, but why not? So infinity is another attractor. And the green side is the basin of attraction of infinity. The blue side inside the unit circle is the basin of attraction for the attractor that is in 0. And there is a border between these two basins of attraction, and this border is called Julia set. Okay, so in other words, so the blue one, so I have 2 points. So this, I define the 0 as attractor A1. I define the infinity as attractor A2. Okay, and then I have a basin. So this is okay. Can you see the basin thing here? Ah, okay, you can see a little bit farther than this line. If you cannot see, yeah, you can see everything. So you can see up to here, basically. So this is basin of attraction for attractor A1. Okay, if any of you does mathematics and have seen some algebraic topology, know what I'm writing here. Okay, so did you ever seen this notation? Can you read it? Yes, this thing here. Did you ever see this? No? Yes? No? No. Anyone seen this? Yes. Okay, Johan. So if you've seen this, this does not mean partial derivatives, even if it has some relation, and it's the boundary, exactly. So this is the boundary of these two sets. So this is the boundary of the basin of attraction A1 is equal to the boundary of basin of attraction A2. And this has very profound consequences. If you have many basins of attraction in your map, all of these basins of attraction have the same border, the same boundary. So the border of all the basins of attraction is the same. This is a theorem that we are not going to explore right now, but it's very profound. It's very profound consequences, and that I will tell you in a second. So all this basin of attraction has the same border, and this border is defined as the Julia set for, let me write it a little bit better. So the Julia set for your function, for your map. Okay, not very beautiful, and it's even more ugly on the. So let's delete this. Let's do it a little bit more compact here. So this is one, and I define all of the border. So all basin of attraction share the same border, and this border is defined as the Julia set for the map F. Okay, so that's the definition of Julia set. And here, now, you can kind of imagine, you can kind of make an intuition on why we start talking about Julia sets when we talk about fractals. So in this case, the Julia set is very simple. It's this square unit circle. It's this unit circle. So that is given by the fact that you have a square. So the Julia set in this case is very, very simple. And now, yeah, I forgot to periodic repelling point. Sorry. Points. So we'll come to it in a moment. Sorry for breaking the rhythm, but I get disturbed when I see something like this. Okay, so this is the Julia set is the closure of all periodic repelling point, and this is given. The closure of the set of all periodic repelling point is the boundary between different basin of attraction. And this theorem that say that all the basin of attraction share the same boundary, it makes you gives you an intuition on the fractal nature of the Julia set. In this case, it's very simple because I just have two boundaries, two bases. I have only two attractors, 0 and infinity, and I have only two bases. So their interface, their boundary, it's very simple. It's this unit circle, and that's fine. Okay, so this is one Julia set. But imagine that you have in 2 dimensions, you have 3 attractors, and you have 3. Therefore, if you have 3 attractors, if you take C different than 0, you will have a situation that would be very difficult to study analytically, but you will have a situation where you have more than 2 attractors. Suppose that you have 3 attractors. And if you have 3 attractors, it means that you have 3 basin of attraction. If you have 3 basin of attraction, then they have to share the same boundary. So you will need to have a situation where the boundary is the set, the closure of the repelling periodic point. So if you sit on the boundary, you stay on the boundary. But if you move slightly away from the boundary, you are forced to go in the direction of one of the attractors. And if you have 3 attractors, so your boundary will not be anymore between 2, but will be, imagine that it is between 3. So now you have to accommodate a boundary between 3 sets in 2 dimensions. So the boundary has to be shared among 3 sets, but in 2 dimensions. And the only way you can do it is by exploiting fractals, because you accommodate this extra space you need in the higher fractional dimension that fractals provide. Okay? So by the fractals build up the interface of the Julia set. Is it clear? It's kind of an interesting point. So the Julia set is fractal. So for this example, is fractal for every z different, well, it's fractal for every z that is different than 0 and -2. That's kind of curious, but that's how it is. So if you pick 0 or -2, in the case of 0, we just demonstrated the Julia set is very simple. It's not fractal, it's just the circle, the unit circle. But if you take -2, you can also demonstrate that it's not fractal. But for any other C, sorry, for every C complex number different than 0 -2, for every other C, then you will find out the fractal boundary. When there are multiple attractors, will there be points between attractors where it does not get attracted to anything, but the point is infinitesimally small given infinite time? The point is a point. So it's infinitesimally small in the sense that it's a point. So here the boundary is made up of points on the same circle. So it's an infinite number of points, but it's still only a set that is one-dimensional in this case. And if you take some point which is on one side or the other of the boundary, then you will be forced, even infinitesimally, then you will be forced in one of the two attractors over an infinite amount of time. And if you have C that is different from 0 or -2, what you have is that this has a very strange shape. We'll assume this fractal shape. And then as soon as you move out of the boundary of the set of periodic repelling points, since they are periodic, the repelling points defined like this, having derivative greater than 1, then you will slide to one of the 3 or 4 or many attractors. So that's the idea. Okay. Good. So you can fairly easily demonstrate the repelling periodic property of this by, you can take it as an example or an exercise, but where do I write it? Let's write it here. So is this clear? Can I delete it? Yes? No? Yes? Yes? Okay. Some people say yes. I trust the people. We love the people. Okay. Let's delete also the equivalent to logistic. Okay. So to demonstrate for, again, C equals 0, to demonstrate it's fairly easy because then your periodic points, what are you searching for are the nth return map of a given periodic point. Well, it's here, right? You're searching for this kind of point. Therefore, if you take C equals 0, you're searching for the Z tilde, so that Z tilde to the 2 n, to the 2 to the n, sorry. Okay, to the 2 to the n is equal to Z tilde. So for the, where n is the return map, okay? For the first return map, then this is only Z equal to Z square and it's a fixed point. But for the second return map, this is Z to the Z to the 4th power, for the third, the 8th power, and so on and so forth. And then we can use the periodic notation that I was writing on the other side. This is equal to the 2nr, that is the module of Z times I theta is equal to the r to the 2n. So if this r is equal to 1, this is also equal to 1. So I cannot care about this. E to the I theta to the 2n. Okay, so when this is periodic, where this is equal to e to the I theta plus 2 pi a certain k, periodic number, okay? Where I get back there after a given number of Lagrangian point. Oh, that's a good point. Okay, so let's do it like this, and then you simply solve this, and you find out the zeta. So maybe since it's Dayon is now talking about celestial mechanics. You are bored, and this is too easy for you, but let's write it nonetheless. So this is given by e to the 2 pi. If you solve this, 2n minus 1. Okay, with k, which is a given periodicity, that will be between 0 and 2n minus 1. Okay, and belongs to the natural numbers. Okay, so now the only thing that you're left to do is to do the derivative for this as z tilde. Yeah, so this is z tilde of the nth vector map. So let's call it z tilde of n also here. And if you do that, then you basically you have to, when you derivate the exponential, and then you get to the n that is definitely greater than 1. So this gives you the fact that the periodic point on the unit circle in this specific case are repelling each other. So you are on the set of the repelling periodic points, so you're on the Julia set. And this is also equivalent to the boundaries between basin of attraction. Okay, so the lecture is basically finished, so I don't have the time to do the Mandelbrot set. I will do it basically next time, and I will show you some animation, but that's very easy to see. One point that you are raising, if you have any question, you can write it in chat or speak, but one point that Dayon is raising is that you think about Lagrangian point in celestial mechanics. And that's exactly what we will see in our last or second to last lecture, where we will connect all of these to conservative systems, so to Hamiltonians, and the fact that you have periodic points in Hamiltonians that gives you the orbit, and then any point outside of the orbit it is at high risk of becoming unstable. And this reflects into the motion in the solar system, for example. So you have a lot of chaos that you can observe in the solar system, on the asteroid belt, on the motion of satellites in complicated n-body systems like Saturn or Jupiter. And there is plenty of things to connect from these very mathematical and fairly abstract object to the physics of many systems that we study. So thank you very much. Do you have further questions? Do you have questions? Okay. So let's
start recording. Very good. Okay, so welcome again. And we've just seen the Cantor set and the staircase as an example of a fractal and how fractal can be used to make up functions with some proper maps and functions with some interesting properties. So the staircase is a very used mathematical counterexample because it's continuous, is derivable almost everywhere, and is monotonically increasing, but nonetheless has an infinite number of discontinuities. And not only this, but is monotonic, but the derivative is 0 almost anywhere. So that's that's a pretty interesting mathematical object. And then we've seen the complex maps and how this relates to the Julia set. So now I want to share my iPad. Okay, so I hope you see my iPad. So this is the lecture before, and about the definition of the Cantor set. And then I use the whiteboard, so there is not much time, not much notes regarding that. Okay, so okay, my pen is not working. Why it isn't working? I hope it has charge. It had charge yesterday. So let's see. Okay. And another thing we've seen is how fractal relates to complex maps. So when you do a non-trivial complex map, fractal appear very often. So complex maps are basically just maps. So I define an object where different iterations can be seen by applying a function. The only difference is that this time the function does not go from the real number to the real numbers, but from the complex numbers to the complex numbers, okay? And then you have the usual definition of fixed point, where the application of the function will give back the same point, and periodic point, that I denoted with tilde, if I remember correctly, where if I apply the nth return map, this f is only the first return map. If I apply the nth return map to a periodic point, then I will get back my periodic point. So this is n periodic. And then if I take the repelling periodic point, I can define the Julia set. So let's see, yeah, let's write it. It's probably easier if I do it like this in a rush. So you will have it here on the notes. So this is the repelling periodic points, and the Julia set, let's do it in this blue color. So Julia set is the closure of the repelling periodic points and if we take, for example, this complex map, z squared plus c, then this is equivalent. This is called the quartic map. And this is equivalent to the logistic map in the real number logistic. So the two have a one-to-one correspondence if you sit on the real number, on the real axis. So if we consider c equals 0, then we had these conditions, and we've seen that for c equals 0, this map, let's see if I can do a decent, yeah, okay. So this map has, so let's try to do this like this. If we consider c equals 0, it's even worse if I asked it to do a proper circle, because it's not centered, and this is even more disturbing. So, but okay. I'm better at drawing on the whiteboard, I think. I'm not very good, but I'm a little bit better. But let's suppose that this is the unit circle. So So this is the unit circle, and then we have here a fixed point, and then all this region is basin of attraction B of the fixed point A1. And then we have another fixed point at infinity, A2, and the basin of attraction of infinity is everything with outside of the unit circle, and this is B of A2. And then we found out that the Julia set of a given function is given by the border of the different basin of attraction. And all the basin of attraction in this complex map share the same border. In this case, it's only 2, and so this makes it very trivial. So the border is just this, the unit circle. But in the case that there are many, then they all have to share the same border, and this is what gives you fractals. So we've basically arrived to this point, and then we have to define the Mandelbrot set. Before doing that, I want to show you a very nice website that an old student of Lund did. So this website is malinc.se. So Malin Christensen, she did this very nice website. She was a student in mathematics in Lund some years ago, and then she was teaching assistant, but I cannot get a hold of her. This was before my time. So this is basically the Julia set, and this is an animation, and I can show you a little bit better like this. So this is the Mandelbrot set that I will define in a moment. But before defining the Mandelbrot set, this is a demonstration of the Julia set. Where I put my mouse, it's C. So if I put my mouse, do you see my mouse as well? Do you see the website and my mouse? Yes, no? Are you sleeping, all of you? Yes. Are you sleeping? No. Okay. So I hope you see my. If you don't see my mouse, I hope let me know. But so if you see the website and my mouse, you can see where my mouse is pointing. This is basically the C factor of the Julia set. So if I put it here, roughly, then the C factor is equal to 0. Okay. Here is where C is equal to 0. And then when I move my mouse, I will move C. So if I go up here, C will get some imaginary value. If I go down, we'll get a negative imaginary. If I go in this way, it will get a real value. And if I go that way, we'll get a real value, okay? So this is the complex plane, and I move around the 0. And as you can see, in 0, I mean, I cannot find the 0 exactly. There it was. So this is roughly the 0, and it's the unit circle, the Julia set, because it's the boundary between the two bases of attraction. As soon as I move out of the 0, then as you can see, it gets quite distorted. And maybe you cannot appreciate because of the resolution of the screen or of the streaming, but you can see that this is not simply a deformed circle. These are some structure that at a very small scale, these are some structure there. And this is the fractal patterns that emerge as soon as you move out of 0. And these fractal patterns will be very, very small. So the fractal dimension of this object will be very, very close to 1, but will not be 1 and will not be 2, will be something in between, will be 1.001, will be very small and close to 1. But this is already an indication of a fractal. And if you move very much out, then you see something that is really a fractal. Okay, there is no doubt that this is a fractal, for example. And if you move out again, you see that the Julia set becomes not connected. So you have different instances of the Julia set. This is still a fractal, but this fractal will be not connected. So we'll have separate instances. And these instances will repeat itself in a fractal pattern. So this you can see that you have these kind of strange shaped structure with these that are like leaves-like structure that repeat itself over and over. So you have a series of non-connected sets, and this generates your Julia set. So when C is a big number like this, what it means is that you have very many bases of attractions. And when the number of bases of attraction gets large, then your fractal dimensionality increases to the point that you start having non-connected sets. So this is a beautiful website where you want to play a little bit. And now we can very easily define the Mandelbrot set. So the Julia set, it's, oh, look at this beautiful one that I just stumbled upon. So of course, this is very nice and very fascinating because you stumble upon beautiful shapes without even knowing. So there was an interview that I found in on YouTube about the science fiction author Arthur J. Clarke, that he wrote The Sentinel, for example. And so it's a very famous science fiction author. And he was interviewed by, probably by Asimov. So it was this kind of 80s big personality interview among people were writers, were artists, no? But fascinated with technology because they were science fiction writers. And the hobby of Clarke was to zoom in the Mandelbrot set to an infinite degree of accuracy. So you zoom in and zoom in, you continue to see fractal structure, and they will be very different because they will be based on the Julia set, basically. The Mandelbrot set is a specific example of Julia set, and this is fascinating and it's artistic. So it has this quality, this artistic quality of mathematics to it. And okay, but apart from this, so you see that you can stumble upon very beautiful fractal patterns and shapes. So here you see that you go from a non-connected Julia set to a disconnected Julia set. So in a small, you kind of fold it into separate Julia sets. And the difference is that the Julia set can be done with any map. So any complex map has a Julia set. This can be fractal or not, depending on your map, on the complexity of it. And that's fine. It's related, in fact. If the map is chaotic, then its Julia set will generate a fractal pattern. Otherwise, no. So if you take a simple linear map, you will not see beautiful fractal patterns, but you will still have a Julia set. However, the Mandelbrot set is a specific example of Julia set. So now I'm jumping between shares. I hope I'm not breaking the rhythm, but that's fine. Okay, so I wanted to share my iPad again. Okay, there it is. Good. So the Mandelbrot set is, of course, is one of the most famous fractal pattern in general, and of course is the most famous fractal map. So the Mandelbrot set is the union of all connected. So you remember the definition of connected, that you can see that some Julia sets were splitting into separate Julia sets, and others were just one boundary. So if the Julia set has only one boundary, it can be defined as one boundary of a single not of a single, that's difficult. But if the Julia set can be defined as one boundary, then it's connected. And therefore, the Mandelbrot set is the union of all connected Julia sets but only of the quartic map. So it's a special case. Julia set can be calculated for any f, but the Mandelbrot set is the union of all connected special Julia sets that are connected of this special function z square plus c. And this is Mandelbrot of C, basically. So you have this shape of the Mandelbrot set will be given by the union of all these Julia sets. So sometimes very often actually you see the Mandelbrot set painted with beautiful colors, but basically this is the proper definition of the Mandelbrot set is just a yes or no. Does this point in C belongs to generate a connect Julia set? If yes, then this point belongs to the Mandelbrot set. If not, then this point does not belong to the Mandelbrot set. So in the same way that I've shown you before. So let's share it again. So share again my Google thing. Okay. Okay. So this is the Mandelbrot set, very famous Mandelbrot set. And if I pick a point inside the Mandelbrot set, I will have this point will be the C value of the corresponding Julia set, which is connected. So as you can see, if I pick any point in the black shade, that is the Mandelbrot set, I will generate a connected Julia set. This is connected, and now as soon as I move out, this will not be connected anymore. You see? So just go, and when you go outside of the Mandelbrot set, this will not be connected. So that's basically the definition. And since the Mandelbrot set, it's the union of all connected Julia set for the specific quartic map, and since the quartic map is the complex extension to the logistic map, it means that the Mandelbrot set is related to the logistic map. And how it is related? Well, as you can see, these very interesting points here around the real axis, where you have these bulges that collect here. So these are exactly the bifurcation point in the logistic map function, okay? So C has the role of R in the logistic map, and the Mandelbrot set, therefore, is connected to the logistic map in this specific way. And then you can see many very nice animations. And then pretty often, let's see if I can find it. I don't remember if I can find it here. Probably yes, there it is, the Mandelbrot set. Pretty often you find the Mandelbrot set with these beautiful color shapes. So this is what our friend Arthur J. Clarke was exploring. And as you can see, you can do these sort of zooms, you see? And you can zoom in forever and continue to see these fractal patterns. And this is precisely what Arthur J. Clarke was doing, just zooming and tripping, probably assuming some substance to help find beauty in this. But apart from this, that I do not suggest you to do, because I'm a professor in an established institution. But apart from these notes of color, the colors that you see here usually represent how fast this point goes to infinity. So if you remember, you had the Julia set, if you pick a point outside of the Mandelbrot set, so here in the beige zone, if you pick one point there, it means that the Julia set is disconnected. And then if you take one point basically everywhere in the Julia set, usually it's calculated from 0. So if you take one point in 0, you start from 0 and then you iterate, this will go to infinity pretty quickly because it's a square law. And since the Julia set is not connected, it means that 0 will now go to infinity. And this is, in fact, this is another way you can define a Mandelbrot set, by looking at all the Julia sets in the cases where the f of 0, the quartic map calculated in 0, does not go to infinity. If it does not go to infinity when you iterate, then it belongs to the Mandelbrot set because it means that it is inside a connected Julia set. If it goes to infinity, it means that the Julia set is disconnected. You have way to escape in a certain sense. And it means that the basin of attractions are only at infinity. So as soon as you put it anywhere that is not the precise border, so numerically, as soon as you put it anywhere, this will go to infinity. So this is another way that you can define the Mandelbrot set, in fact, and it's a very formal, it's a formal way of defining it, more than maybe a little bit more formal than the qualitative way I did. But it's the way that is computationally useful. So because this is how you calculate the Mandelbrot set. You take f of 0, and then you iterate the Julia set. You iterate the quartic map, and you find out if this point goes to infinity or not. And if it does go to infinity, you paint it in different colors according to how fast this is going to infinity. So this is the different colors of the Mandelbrot set. What does the different colors of the Mandelbrot set mean? So this is basically it, okay? And so here on the website, there is also an explanation. One way that you can do it, that we suggest you to do it if you want to try it. This is a very fun thing to program because it's fairly easy and you get these beautiful pictures. Of course, Malin did it extremely nicely, and you can see this application is well done because it's easy to use and it's fast. But without having this pretense of making something this interactive, this advanced from the computer science point of view, you can make it very easy, and the way you make it is precisely this. And you can use, we suggest you to use in the book, the Newton-Raphson method that finds the zero of a function and therefore finds if a given function is going to infinity or not. And so by applying this Newton-Raphson method in an iteratively way, then you find out everything. So I think that's everything for the fractal. Do you have questions regarding fractals? The Mandelbrot set, the Julia set, the Cantor set. As you can see, there are plenty of sets in fractals. No questions? Okay. Let me then stop the recording.